Good evening, all. Hello.
Good evening, sir.
Yeah.
Good evening, sir.
Good evening. My voice is audible to you all?
Yes, sir.
Yes, sir.
Right. Then, in continuation to the previous chapter, that is terpenoids and terpenes and terpenoids. In that, the first, after the introduction, we're going to discuss about the structure determination of some terpenoid and terpene and terpenoid compounds. Okay. In that first one, you take alpha terpenol. This is the terpene. Yeah. Previously already given structure. Again, I'm going to give you that structure. Is the structure of this is the structure of alpha terpenol. It is a colorless liquid. It is a colorless liquid. It is isolated from turpentine oil. Isolated from pine oil and a turpentine oil. From these two sources, that terpenol is isolated. It is optically active. Optically active. What is the optical active center here? Look at here. Optical active means at least two optical chiral centers are existing, right? This is the optically active center. Center is this is the center. It is the optically active center. Then come to the structure elucidation. Structure elucidation of alpha terpenol. How this is the known structure. It is actually the structure I am giving to you. Now nowadays it is known, but whenever we are isolated this turpentine alpha terpenol from the turpentine oil and pine oil, we don't know the structure. In the earlier days, at the initial stages, they don't know the structure. Then how to determine the structure? These are the following steps to determine the alpha terpenol structure. For determining structure, the first requirement is molecular formula. Molecular formula C10 H18O. This is the molecular formula. But simply we are observing this molecular formula. It indicates that from the classification of this terpenes and terpenoids. Then what is that? It is a simple terpene or monoterpene. It indicates that it It is a monoterpene. Right. Then from this molecular formula, it indicates that it is monoterpene. It is monoterpene. Right. Now, previously in the case of structure discussion, here I am discussing the structure of this. Just a minute. Yeah. In the structured discussion, we are giving the statement. It is optically active. Here also that is important. From the physical observation, it is easily find out whether we know the structure, we don't know the structure. It is not dependent because once you find or we are isolated the molecule from the natural resources, we can identify some physical properties without knowing the structure. In that, optical activity is one of that. Simply, we can prepare the solution of that compound, put into the polarimeter, then observe the optical rotation. Once it is that plane polarized light is rotated by the molecule, then that is optically active. If it is not rotated, there is no change in the plane polarized light intensities or rotations, then it indicates that optically inactive. But in the alpha terpinol, it is optically active, means it rotates the plane polarized light. Then it is optically active. Optically active. Just here we are seeing the structure, but whenever we don't know the structure, how to do this process? Okay, optically active. Then, therefore, the structure of alpha terpinol must have at least one chiral center. Once it becomes optically active, it is existing with at least one chiral center. Therefore, the alpha terpinol existing with one chiral center. Existing with one chiral center. Right. This is about the simple observations from the molecular formula and nature of the compound by same simple physical properties, right? Just a minute, I will start the second year class. Someone is started the second year class. I need to put the recording. Just a minute. Yeah, sorry for the interruption. Okay, this is about the simple physical properties and molecular formula. Now coming to second one. Second point. This is the first point. You are knowing about the molecular formula and its optical activity nature. Next, alpha terpinol. It's, you know that alpha terpinol. It is treating with, you know, the molecular formula C10 H18O. Then it is reacting with acetic anhydride. The acetic anhydride, this one. Suppose this is the acetic anhydride. Oxygen, it is also oxygen. C-double-O, C-H. This is acetic anhydride. We call it as acetic anhydride. Or we can also show like this Ac2O. Then it is reacting with this acetic anhydride whenever we are heating or boiling it with. It leads to the formation of alpha terpinol acetate. This alpha terpinol acetate. What is that? What is that indicating? Suppose if any molecule having OH group that is reacting with acetic anhydride undergoes acylation reaction that leads to the formation of an acylated or acetate product. This is the acetate from alcohol. Now this reaction indicates that. What is this reaction indicating? This reaction indicates that alpha terpinol is existing with one hydroxy group. Simpler, it indicates that alpha terpinol is existing with one OH group. Then this OH group is what type of OH group? You know that OH group may be a primary alcohol, or it may be a secondary alcohol, or it may be a tertiary alcohol, or it may be a phenolic alcohol. Phenolic alcohol means it is maybe a phenol. Therefore, the four types of OH groups are there. One is primary, secondary, tertiary, and the fourth one is phenolic. Then we need to find out what its nature is. Now, I'm going to do next reaction, that is alpha terpinol is subjected to phenolic reactions. What are the phenolic reactions? A Lieberman test, Thalic fusion test, and FeCl3 test. All these tests are phenolic tests. Now this alpha terpinol is subjected to this phenolic test. It shows negative tests for phenolic group. Phenolic OH group. Therefore, it indicates that OH group is attached with aliphatic carbon. But not with aromatic ring, aromatic phenolic ring or phenyl ring. This reaction clearly that the OH group is a aliphatic OH, right? Next. Next here. If alpha terpenol on oxidation, third one, this is the third reaction. Alpha terpenol on oxidation, using there are several kinds of oxidations. You can any oxidizing reagent is an oxidation. It gives a mixture of carboxylic acids. A mixture of carboxylic acids. Why this alpha terpenol produces a mixture of carboxylic acid? Look at here. This is the primary alcohol. Whenever it is an oxidation, whenever we are subjected to an oxidation, it leads to produce monocarboxylic acid. Only one compound is generated. Simple. One carboxylic acid is generated. One carboxylic acid. When we are taking primary alcohol. Similarly, you take a secondary alcohol. Secondary alcohol. Sorry. You take secondary alcohol, it leads to produce two compounds. Suppose this is R and R prime. R and R prime. First, it is on oxidation. First, it generates to ketone. Later, this bond will undergoes the oxidation that leads to formation of RCOOH plus RCOOH. Two different carbons containing carboxylic acid. Mixture of carboxylic acid. Mixture of carboxylic acids. Similarly, you take tertiary carboxylic acid. R prime, R double prime, OH, which is on oxidation, then directly it produces RCOOH. A 3 carboxylic acids are generated. 3 carboxylic acid mixture is generated. Right? Now, from this reaction, if you coming to this one, from this reaction, this alpha terpenol is an oxidation, subjected to an oxidation that leads to formation of a mixture of carboxylic acids. Then it indicates that this reaction indicates that the OH may be the OH group may be yes. Here a mixture of carboxylic acids. But here, whenever we are coming to secondary alcohol, it gives 2 carboxylic acid. Whenever 2 carboxylic acids are generated, we can easily find out. More than 2 carboxylic acids are generated, that is called mixture of carboxylic acids. Therefore, it indicates that alpha terpenol is attached with tertiary alcohol. Tertiary alcoholic group. Alcoholic OH. OH group. Tertiary alcoholic OH group. Now the presence of OH group, that is tertiary alcohol, is confirmed. Next, fourth one. You come to fourth one. Alpha terpenol is subjected to bromination reaction. It is an addition reaction actually. Bromine addition reaction. Then it leads to produces dibromo alpha terpinol. Dibromo alpha terpinol. Look at here. Here its molecular formula is C10H18O. Then the dibromo alpha terpinol is C10H18O Simple addition reaction. When the addition reaction takes place, when the addition reaction is taking place, this alpha terminal or any other substance, if it is the substance is having one double bond, it undergoes bromination, bromine addition, that leads to the formation of dibromo product. It is undergoing addition reaction with bromine that leads to the formation of dibromo product. Right. Suppose if two double bonds are there, Now, look at here. This is the two double bonds are there in the molecule. Or instead of that, triple bond is there. In a triple bond is there. That is undergoing addition reaction with 2 moles of bromine. That leads to the formation of tetrabromo products. The tetrabromo products, if it is the alkyne, a triple bonded compound, that leads to the formation of this kind of bromine product, tetrabromo product. Or it is having two double bonds, the two double bonds undergoing the addition reaction that leads to the formation of tetrabromo product like this. Both are tetrabromo products. But here the alpha terpinol is producing only dibromo alpha terpinol. Therefore, it indicates that this reaction indicates that alpha terpinol containing one double bond. Containing one double bond. There. Next, coming to the next point. Look at here. This is the C10H18O alpha terpinol. Now we are adding one molecule of bromine. That leads to the formation of C10H18OBr2. Then it is more equivalent to one OH is there, tertiary OH group is there. Then C10H18, that O is in the form of 18, OH form. Therefore, CH17.
OH.
Br. Now, this is the fully saturated structure. Suppose this is also attached with a single bond, therefore, it is also treated as hydrogen. These two bromines are also treated as two hydrogens. The fully saturated structure is C10H20. C10H20. Now, this one is resembles to CnH2n. CnH2n. When? What is the use of this CnH2n? Whenever these are the common formula or general formula, CnH2n indicates the monocyclic system. Monocyclic system or monocyclic ring. If it is CnH2n minus 2, right? Bicyclic. H2N minus 4 tricyclic. Okay, it is. Now from this CnH2n, that is C10H20, indicates that alpha terpinol is a monocyclic monoterpenoid. Therefore, alpha terpinol is a monocyclic monoterpene. Terpenoid. Right. We clearly understand that in the alpha terpinol is having one ring. Okay, that ring system is how, what is the type of the ring system? Now coming to sixth one, size of the ring. Size of the ring. Now, a simple reaction can give the size of the ring. There is alpha terpinol. This C10H18O is subjected to reaction with concentrated H2SO4. This concentrated H2SO4 is reacting with alpha terpinol. Then it undergoes the dehydrogenation, not the dehydration, dehydrogenation reaction taking place. That is called aromatization. It undergoes the aromatization that leads to the formation of a known compound, that is parasamine. This is the known structure, right? The generation of parasamine indicates that the monocyclic system is a 6-membered ring. In that, alpha terpinol is also having a methyl and isopropyl group. These methyl and isopropyl groups are substituted on the 6-membered ring in such a way that 1,4 position relationship. The formation of parasamine indicates that all these factors. What is that? Parasamine is a known structure, already known structure. It generated from the alpha terpinol and treating with the concentrated H2SO4. Therefore, after formation of this parasamine skeleton indicates that alpha terpinol is existing with the parasamine skeleton. Once it is existing with parasamine skeleton, it is existing with the 6-membered ring system. 6-membered ring system. And second one is, in parasamine, methyl and isopropyl groups are, these are the methyl and isopropyl group. This is the methyl group. This is the isopropyl group. CH3, CH2, CH3. This isopropyl in the parasamine, methyl and isopropyl group present on this 6-membered ring indicates that methyl and isopropyl substitutions are present in the 1,4 position relationship of the alpha terpinol 6-membered ring. Right? These three conclusions you need to write here. Right there. Parasamine. Parasamine is a known structure. The formation of parasamine indicates that formation of parasamine indicates that first one, alpha terpinol is existing with six-membered ring. Next, second one. On the 6-membered ring, and the 6-membered ring. Methyl
group and isopropyl groups are present.
This is the isopropyl group.
CH3, CH2, CH3.
Yes, this is the isopropyl group. This is the attachment. This one. This group is the isopropyl group. This one is the methyl group. Isopropyl. Okay. And the 6-membered ring, methyl and isopropyl groups are substituted 1,4 position. 1,4 position. Based on these conclusions, are based on these evidences, the partial structure of alpha terpineol is existing with a 6-membered ring. Then in the 6-membered ring, the methyl group at first position, isopropyl group at 4th position. Right. Next, in the previous reactions, it is alpha terpineol is existing with one tertiary OH group. We don't know the position, and one double bond, one CC double bond. This is the partial structure of. In this partial structure, we know the ring size and positions of the methyl and isopropyl groups, but we don't know the positions of tertiary OH group and C double bond, right? Now, further, to identify the positions of that tertiary OH group and double bond, we need to do a degradation experiment. Position of C double bond and tertiary OH group. Yeah. For that, the position of C double bond C and OH group inferred from the oxidative degradation experiment. Oxidative degradation experiment. That what is going on? First, you take alpha terpineol. What is the molecular formula? C10H18O. Now, which is subjected to in this with this molecular formula. What are the functional groups are there? We know C double bond C and one tertiary OH group in that, which is subjected to oxidation with 1% alcoholic alkaline means basified. We are KOH. This is a step 1 reaction. That what's happening here, whatever the double bond present in it, it is reacting with KOH. It leads to the formation of diol. It's converting into corresponding diol. Right. Now here also this double bond which is present in the alpha terpineol is converting into diol. Already one OH group is there. 2 more OH groups are generated. From that, the product is trihydroxy compound or derivative. In this trihydroxy compound, what is the molecular formula? C10, He18, and O3. In that, 1,2-dihydroxy fragment along with tertiary OH. 3 hydroxy groups are there. Now, this OH3 OHs are subjected to oxidation with chromic oxide, Cr2O3, in acetic acid. This is the step 2. What's happening then? One of the hydroxy group is converting into keto. One of the hydroxy attached carbon is converting into carboxylic acid, and another one is remaining unchanged. Remaining one is unchanged. That is, it leads to the formation of keto hydroxy acid derivative is generated. Look at here. One keto is generated, one acid is generated. One hydroxy remains unchanged. Okay. There. What is the molecular formula again? It's keto hydroxy acid C10, He18, O4. In that, what are the functional groups are there? One keto group is there, C double bond O. One carboxylic acid is there, along with one tertiary hydroxy group is there. The tertiary hydroxy group is unreacted. Right? Next, which this compound undergoes spontaneous lactonization. Spontaneous, this is step 3. Spontaneous, sorry, spell correction. Spontaneous lactonization. Then it leads to the formation of that lactonization is taking place. Suppose, what is the lactonization? Suppose it is a long chain system. At one position, OH group is there. At one position, carboxylic acid is there. Now, these two are undergoing dehydration. Then it leads to the formation of C double bond O. That it is cyclic ester. Lactam is the cyclic ester. The cyclic ester is generated by the relieving of or by the elimination of one water molecule. This is also undergoing spontaneous lactonization, means leaving the one water molecule, that leads to the formation of cyclic ester. That is keto lactone. It is keto lactone, right? I want to remove this. If you want to, you can write it. Right. This ketolactam, what is the molecular formula? One water molecule is eliminated from that. From the above formula, you remove one water molecule, H2O. Two hydrogens are reduced and one oxygen is reduced. That is what is the molecular formula? C10, H16, O3. Now, what are the functional group present in it? One keto group is there and one cyclic ester. This is a cyclic ester. Like this. This is the cyclic ester. These are the functional group present in this ketolactone. Right? This ketolactone further treated with warm alkaline KMnO4. Warm alkaline KMnO4. It is the oxidizing agent, mild oxidizing agent. It is the step 4. Then what is the thing happen here? This ketolactone is converting into two molecules. One is acetic acid. One is acetic acid, and another one is terpenoic acid. Terpenoic acid. The terpenoic acid molecular formula C8H12O4. C8H12O4. Again, it is treated with KMnO4, that is neutral KMnO4. Just dissolve one water, that is used for the oxidation reaction. Again, it is also oxidation reaction. There is step 5. Then what are the product it is generated? Terbic acid. Terbic acid. Then what is the formula? C7H10O4. This is the known structure. The terbic acid is the known molecule. It is already known structure. The terbic acid molecule is at the time of the structural elucidation of alpha terpinol. The terbic acid structure is known. What is the degradation? First, I forgot to tell you. What is the degradation? Degradation is simple. You cut into the pieces, into smaller parts. Similarly, here a large sized structure is there. That is treated with some chemical reagents, cut down into the smaller fragmented or smaller molecules. By analyzing these all the smaller fragments, we can find out the structure of a bigger molecule. Here also, this is the oxidative degradation. Oxidative degradation means we are applying some oxidation reactions on the molecule. That molecule is degrading into the smaller molecule. Those smaller molecules are analyzing, by which we can find out the structure of that compound. Here also, we are treating the alpha terpinol into with a different oxidizing agent that will be converting into terbic acid. This is the last structure. This structure is already known at the time of the alpha terpinol structure initiation. What is the structure of terbic acid? This is the terbic acid. Simple. This is the terbic acid. Right. Now, simply we can analyze this terbic acid in the reverse manner, retrosynthesis manner. Now, we come back. From what is the difference between the terbic acid and terpenoic acid? There is a 1 CH2. The elimination of 1 CH2, that is the analog carbon is removed, that leads to the formation of this terbic acid. Means the difference is only 1 CH2 between the terpenoic acid and terbic acid. That indicates that the higher member carboxylic acid is converting into lower member carboxylic acid. From that, we can find out. We can easily find out that the structure of terpenoic acid is. This is the structure of terpenoic acid. Only difference is 1 CH2. You are adding 1 CH2 in between the carbon of this carbon and COH. Now, this is the terpenoic acid. Look at here. Just this difference is identified based on the molecular formula. Here it is the C8H12O4. It is the C7H12O4. The difference is only one CH2 group. Therefore, higher carboxylic acid is degraded into lower carboxylic acid. That is only difference is one carbon. Now I am adding one carbon in between the carboxylic acid group and the cyclic group, 5-member ring. That leads to the formation of terpenoic acid. It is the retrosynthesis. I mean, I am analyzing in back from the back to starting, right? Then, along with terpenoic acid, acetic acid is generated. This is the acetic acid. How this acetic acid is generated? This terpenoic acid and acetic acid is generated from the ketolactam. Here the lactam is unchanged. This is the lactam, 5-member lactam. It is not undergoing any oxidation reaction. Therefore, these two carboxylic acids are generated. When the two carboxylic acids are generated, That molecule is keto group, is having existing with the keto group. Therefore, the compound is what? Ketolactam is. This is the terpenoic acid, terbic acid, terpenoic acid. This is acetic acid. Now, from that, you combine the acetic acid and terpenoic acid at the junction of this acidic group by adding simple keto group. That is, right. You take the same lactam, is coming from that like this. CH2, CH2, C double bond O, C. This is the ketolactam. The ketolactam. Now, the ketolactam is generated from the spontaneous lactonization of this ketohydroxy acid. Then, what is the structure of ketohydroxy acid? Ketohydroxy acid is, just open up this lactam ring. I'm breaking down. Just I'm adding water is removed here. Minus H2O. That means the same water molecule adding here. The OH is adding here. Now it leads to generation of this ketohydroxy compound. EOOH, CH3. You get it. Ketohydroxy acid. This is the keto group. This is the hydroxy group. This is the acid group. Now, where it is coming from? It is coming from trihydroxy acid. So, trihydroxy compound. Therefore, trihydroxy compound is generated from the, look at here. There is a junction point between this carboxylic acid and this keto group. How it is generated? Trihydroxy is converting into ketohydroxy by the oxidation with the chromic oxide. This chromic oxide can oxidize this diol group. Look at here. This is the diol. The diol is, this one is the secondary one. Okay. This one is the secondary one. Now this is the secondary one. This is the tertiary one. Now this bond will be broke down. That will be converting into ketone. From this fragment, it is converting into ketone. This fragment, whatever the secondary group, it is converting into carboxylic acid. That is CH2 group. This one, not the secondary. It is the primary one, actually. Right? Now the structure is like this. OH, OH, and OH. Now this dihydroxy group is generated from the oxidation with the KOH of the alpha terpinol. Now what is the structure of alpha terpinol? Simply OH and double bonds. Now whenever we are analyzing from the end product to the starting product, we can easily find out the structure of alpha terpinol from this degradation. Now from this degradation structure, the structure of alpha terpinol is from this oxidative degradation. Oxidative degradation. The structure of alpha terpinol is this. From the structure, you can redraw the degradation products. You can do yourself by following your book. Okay. Now, finally, the structure of it is very much important. You need to formalize all the degradation products by using this alpha terminal. That is, take the alpha first. This is the first one. I'm going to show you. Later, you need to do in the remaining molecules degradation experiments. This is the alpha terminal, which is subjected to alkaline KOH. It is 1%. Step 1. Right. This double bond is converting into dihydroxy product, which is oxidizing with chromic oxide. In acetic acid. That leads to the formation of right. This is the keto hydroxy carboxylic acid. This is the first product. This is the second product. Now it is undergoing spontaneous lactonization. Spontaneous lactonization. That leads to the formation of
ketolactone.
yes, ketolactone. Three double bond O, 3H3. Yes, two methyl groups here. This OH and this COH undergoing the lactonate helped by the elimination of water molecule. Then it is subjected to the warm alkaline
KMnO4.
alkaline KMnO4 oxidation. Then it leads to the formation of
Torpinilic acid and
oxidation of
acetic acid.
this bond. That leads to the formation of acetic acid from this fragment. Leads to give the acetic acid along with the terpinolic acid. This is the terpinolic acid. This is the terpinolic acid. Again, this terpinolic acid subject to the KMnO4 oxidation, neutral KMnO4 oxidation. That leads to the formation of terbic acid. This is the terbic acid. This is the degradation experiments, degradation products. Degradation products, right? Then, finally, the structure of alpha terpinol can be confirmed by its synthesis. In any structural elucidation, finally its structure should be confirmed by its synthesis only. Finally, the structure of alpha terpinol can be confirmed by its synthesis. Synthesis only. Synthesis of first coming to synthesis of alpha terpinol. For that, I'm going to start tolic acid, paratolic acid. This is paratolic acid. This paratolic acid treating with 1 H2SO4 and the second one potassium hydroxide. Third one, acidified water. Then what's happening? In the first sulfonation, it undergoes sulfonation. SO3H is substituted here. That SO3H will be that sulfonated product will be treated with the KOH, that leads to the formation of a substituted product with the OH. Then, and that is the sodium salt, I think, potassium salt of phenolic compound is generated, which is on neutralizing with the acidified water, that leads to the formation of a phenolic compound. Is the phenolic compound. This phenolic compound, a metal dissolved oxidation, that is a reduction, sodium metal with alcohol, that leads to the formation of reduction of this aromatic system. You can also call as Beach reduction. Now the product is like this. COH. Again, it is treated with PBr3, tribromophosphate. Phosphorus tribromide it is. Then it leads to the formation of bromo product. That OH is substituted by the bromine group. Bromine. That is bromide ion, nucleophilic substitution reaction. Then this product, which is treated with pyridine, simply it eliminates the HBr. Then it leads to the formation of more substituted olefin. It is the more substituted olefin you get here. There is a chance or the formation of this product is also possible. But according to the Sirjoff and Hoffman rule, Sirjoff rule and Hoffman rule, according to the Sirjoff rule, more substituted olefin is the more stable. According to the Hoffman rule, more less stable olefin is the more stable. But this is called orientation of olefins. Sirjoff rule is more successful than the Hoffman. That is the reason, according to the Sirjoff product, according to the Sirjoff rule, the Sirjoff product is more stable than this Hoffman product. Okay. Then this is the major product. Then it is treated with boiling or refluxing in ethanol in concentrated acid. That leads to the formation of esterification of this carboxylic acid takes place. The COOET is generated. Then the COOET is treated with 2 times 2 moles of methyl magnesium bromide. That is the Grignard reagent. Then it leads to the formation of 2 methyl groups are attached to this carbon CH3. This is the product. This is the alpha terphenol product. Now, by comparing the product, synthesized product and isolated product, simply we can confirm the structure of alpha terphenol. Right. Next, coming to structure determination of limonone. It is a small molecule. You can easily find out. We can easily confirm the structure. Later, I will close the class. Then, structure determination of limonone. LIMONENE. Limonene, right? What is the structure of limonene? The structure of limonene is this one. It is very much similar to alpha terminal, but only difference is one double bond instead of tertiary alcohol. Now, where it is occurring, isolated occurrence, it is isolated from, suppose this limonene is isolated, that is in the three forms, the plus limonene, this is based on the optical activity. The racemic mixture also. This plus limonene is isolated from the lemongrass and the orange oil. Right. Next, minus limonene is isolated from peppermint oil. Next, racemic mixture of this limonene is isolated from turpentine oil. Turpentine oil. Okay. Structure determination. In the structure determination, first you coming to molecular formula. C10H16. It is also optically active. Look at here the structure. The same, whatever the optical center present in the alpha terminal, the same center is present in the limonene also. This is the optical center, right? Right. Okay. Next, optically active. That means limonene is existing with at least one chiral center. You write it your one. Right. Next, limonene is treating with 2 moles of bromine. That leads to the formation of tetrabromo limonene. Therefore, it indicates that it existing with 2 double bonds or 1 triple bond. 2 double bonds or 1 triple bond. Right. Next, third one. Limonene is treating with the dilute H2SO4 that leads to the formation of alpha terpinol. Therefore, it indicates that limonene is a 6-membered monocyclic with a methyl and isopropyl in 1,4 relationship. The position of 1 double bond is same with the alpha terpinol. Both is same in the limonene and alpha terpinol. 1 double bond position is same. From this data, the limonene structure can be written as the follows. Right. After this third one, we can write one sentence here. This reaction indicates that limonene has alpha terpineol skeleton. From this, limonene is generated from the dehydration of alpha terpinol. Therefore, the partial structure of lemonine is R structure A or and structure B. These are the two possible structures. Then these two possible structures are synthesized and compared with the isolated one. That is the one option. And the second one, limonene is the optically active. That is almost, if you take the structure A, in the structure A, there is no optical active center. Therefore, the structure A is ruled out. Then when you come to structure B, here the possibility is this is a chiral center. Then from that, the possible structure for the limonene is structure B, not the structure A. Based on that, and also both will give whenever you take this one or this one, both, which is on subjecting to hydrolysis with the dilute H2SO4 that leads to the formation of alpha terpinol. But based on the previous observations, limonene is existing with one chiral center. That one chiral center, there is absence of chiral center in the structure A. There is a presence of chiral center in the structure B. Therefore, the structure A is ruled out. The structure of limonene is structure B. Finally, its structure is confirmed by its synthesis. Synthesis is previously you learned the alpha terpinol synthesis. Take the alpha terpinol from the previous synthesis. Just one step is extended to the alpha terpinol. Then it is subject to the dehydrogenation by simply treating with concentrated H2SO4 that leads to the formation of controlled dehydration leads to the formation of this product. This is the product. By simply comparing the two structures, synthesized one and isolated one, we confirm the structure of limonene. Okay, tomorrow we are going to discuss about the structure of camphor. Right. Now I'm going to conclude the session. Right. If you have any doubts, can feel free to ask. Any doubts?
No, sir.
Okay.